Why do magnets attract? You take two pieces of iron, ordinary iron, and somehow one of them has been treated so that if you bring them near each other, they go clunk. They pull together. Or you turn one around, and now they push apart so hard you can barely get them close. Now here is the question. Why? What is going on between those two lumps of stuff? There is nothing connecting them. No string, no rubber band, just empty air. And yet something reaches across that gap and says, come here or go away. What is that something? And I want to tell you right now, the honest answer is stranger than you expect. Because when you really dig into it, asking why about magnets takes you down a rabbit hole that ends somewhere you did not plan to go. It ends at the edge of what we can explain at all. By the end of this talk, you will understand what a magnet actually is, where the force really comes from, and why the question, why do magnets work, is one of the deepest questions you can ask about nature. You will not get a simple answer, but you will get the true one. And the true one is far more interesting. Let me start with something you already know. You have seen a magnet, maybe on your refrigerator, holding up a grocery list. Maybe a compass needle swinging around to point north. Maybe those little toy magnets that kids play with. You bring two of them together and snap, they stick. Or you flip one over and now they fight each other. You can feel it in your hands. There is a real push or pull there. It is not your imagination. Now suppose a child asks you, why do they stick together? What do you say? Most people try to give an answer in terms of something familiar. They say, well, there is a kind of force between them, like a stretchy, invisible rubber band pulling them together. And that sounds okay for a moment, but think about it. Why does a rubber band pull things together? Because it is made of molecules, and when you stretch it, you are pulling those molecules apart, and they want to go back. So the rubber band pulls because of forces between atoms. But now you have just used atomic forces to explain the rubber band. So when I ask about the magnet, and you say it is like a rubber band, you have explained one mystery by invoking another mystery. You have not really answered why. Let me try a different approach. Here is something remarkable. Magnetism and electricity are the same thing. Now that is a strong statement, so let me be careful. What I mean is this. You cannot have magnetism without electricity. Every magnetic effect you have ever seen comes from electric charges that are moving, not sitting still, moving. That is the secret. That is where it all begins. Let me show you what I mean. Take a wire and run an electric current through it. That means electrons are drifting along inside the wire, moving charges. Now bring a compass near that wire. The compass needle, which normally points north, will swing around and point in a new direction. The moving charges in the wire have created something around them that affects the compass. We call that something a magnetic field. So moving electric charges create magnetism. That is fact number one. Now here's fact number two. If you take a charge and put it in a magnetic field, and the charge is moving, it feels a force, a sideways force. Not toward the source of the field, not away from it, but perpendicular, at right angles. It curves. This is strange. This is not like gravity, where things fall straight down. This is something else entirely. A moving charge in a magnetic field gets pushed sideways. So we have two facts. Moving charges create magnetic fields. Moving charges feel forces from magnetic fields. Put those together and you start to see something. Two wires with currents in them, each one makes a magnetic field, and each one has moving charges that feel the other's field. So they push or pull on each other. If the currents flow the same direction, the wires attract. If the currents flow opposite directions, the wires repel. You can do this experiment. It works. But wait, a bar magnet, the kind on your refrigerator, has no wires, no battery, no current flowing through it. So where are the moving charges? Now we get to the really interesting part. Every atom has electrons. Those electrons are doing two things. First, in some rough sense, they are orbiting the nucleus. They are moving around. A moving charge. That is a tiny loop of current. That is a tiny magnet. Second, and this is the strange part, electrons have something called spin. Now, spin is not exactly like a spinning top. It is a quantum mechanical property. We call it spin because in some ways it acts like the electron is rotating, but you should not picture a little ball twirling around. It is more subtle than that. What matters is that this spin gives each electron a tiny magnetic field of its own, as if it were a little bar magnet. So every electron is like a microscopic magnet, partly because it is moving around the atom, and partly because of this intrinsic spin. In most materials, these tiny magnets point every which way. Random directions. They cancel out. You add up 1 billion tiny magnets pointing randomly, and you get 0. No net magnetism. But in certain special materials, iron being the famous one, something different happens. The atoms line up. Their little electron magnets all point the same direction, at least in patches, in regions we call domains. And when you magnetize a piece of iron, you are getting all those domains to line up together. Now you have billions upon billions of tiny magnets all pointing the same way. Add them up, and you get a big magnet, a bar magnet. So the force between two bar magnets comes from all those lined up electron magnets interacting with each other through their magnetic fields. And those magnetic fields exist because the electrons are moving in the sense that they have this quantum spin property and in the sense that they have orbital motion. Let me pause and make sure this is clear. Suppose I am explaining this to a bright 12-year-old. I would say it like this. A magnet is a piece of metal where the atoms have decided to all point the same way. Inside every atom there are electrons, and each electron is like a tiny magnet. Normally they point randomly and cancel out, but in a magnet they cooperate. They line up, and when two big magnets get near each other, all those tiny lined up electron magnets feel each other, and they either pull together or push apart depending on which way they are facing. That is the picture. But now I have to be honest with you about something. I have explained magnetism in terms of moving charges, and moving charges come from electrons, and electrons have spin and orbital motion. But why do moving charges create magnetic fields in the first place? Why does spin exist? Why do electric and magnetic phenomena interact in this particular way? And here's where we reach the edge. In physics, we have equations. We have Maxwell's equations that describe exactly how electric and magnetic fields behave. We have quantum mechanics that tells us about electron spin. And these equations are fantastically accurate. They predict the results of experiments to 10 decimal places. They work. But the equations do not tell you why they are true. They describe nature. They do not explain why nature chose those rules instead of some other rules. This is a point that people often miss. In physics, when you ask why, you are usually asking for an explanation in terms of something else, something more fundamental. Why does the ball fall? Because of gravity. Why is there gravity? Because mass curves space-time. Why does mass curve space-time? Because that is what Einstein's equations say. Why are Einstein's equations true? At some point, you run out of deeper levels. You reach bedrock. And the bedrock is, this is what we observe. These are the patterns. We describe them. But we cannot explain them in terms of something more familiar, because this is the foundation. Magnetism is like that. We can explain it in terms of moving charges and quantum spin. We can write equations. We can make predictions. But if you ask why moving charges create magnetic fields, the deepest honest answer is that is one of the fundamental patterns of nature. We do not have a simpler explanation. We have reached the bottom. Now this might sound unsatisfying. You came here wanting to know why magnets attract, and I am telling you that at some level we do not know why. But let me say this, that is not a failure, that is honesty. And it is also thrilling, because it means you have touched something fundamental. You have reached down to the foundations of the universe and put your finger on one of the basic rules. That is not nothing. That is everything. Let me address a common misconception. Some people think that if you cannot explain something in everyday terms, it means you do not understand it. They want me to say the magnetic force is like a stretchy rubber band, or like two people pulling on a rope, or like water flowing downhill, something from ordinary experience. But here is the problem. The magnet is not like those things. The magnetic force has no analogy in your everyday life that is exactly right. When you try to force an analogy, you end up misleading yourself. The magnetic force acts at a distance, through empty space, without anything touching, and the direction of the force is perpendicular to the motion. What in your kitchen behaves like that? Nothing. So, the honest thing to do is to let the magnet be itself. Accept that it is a new kind of phenomenon with its own rules. Learn those rules. Get comfortable with them. And after a while, magnetic forces will feel just as intuitive as rubber bands, because you will have built new intuition. Let me take you on a little thought experiment. Imagine you could shrink down, way, way down, smaller than a cell, smaller than a molecule. You are now the size of an atom floating inside a piece of iron. What do you see? Do you see a nucleus at the center, heavy, made of protons and neutrons? Around it, electrons, not orbiting in neat little circles like planets. No, quantum mechanics tells us they exist in clouds, in probability distributions, in fuzzy regions of space where they might be found. And each of these electrons has its spin, this intrinsic angular momentum, this tiny magnetic moment pointing in some direction. Now look around at the neighboring atoms. You notice something peculiar. The spins of the electrons in one atom are lining up with the spins in the next atom. There is a tendency for them to point the same way. Not because of the magnetic force directly. That is too weak. Something else is going on. It has to do with quantum mechanics, with the way electrons share space, with something called the exchange interaction. The rules of quantum mechanics say that electrons with parallel spins behave differently than electrons with opposite spins when they get close together. And in iron, the energy turns out to be lower when nearby spins are parallel. So they line up. This is the origin of ferromagnetism. It is a quantum effect. Without quantum mechanics, you could not explain why iron is magnetic and copper is not. Classical physics, the physics of Newton and Maxwell, predicts that no material should be permanently magnetizable. It took quantum theory to understand why certain materials are magnets. So when you hold a bar magnet in your hand, you are holding a quantum mechanical object. The force you feel is a consequence of how electrons obey the laws of quantum physics. You are touching the quantum world with your fingers. All right. I promised I would keep the math light, and I will. But let me just mention this much. There is an equation that captures how a magnetic field pushes on a moving charge. The force is proportional to the charge, proportional to how fast it is moving, proportional to how strong the magnetic field is, and the direction is sideways, perpendicular to both the velocity and the field. If you point your right-hand fingers in the direction the charge is moving and curl them toward the field, your thumb points in the direction of the force. This is the right-hand rule. It sounds arbitrary, and in a sense it is. Nature chose to make it work this way. We describe what nature does. We do not dictate it. The key point is that magnetism is inherently connected to motion. A charge sitting still feels nothing from a magnetic field. It has to be moving, and the force it feels is sideways, not forward or backward along its path. This is what makes magnetic phenomena so different from gravity or electrostatic attraction. It is a whole different geometry. Now, let me step back and think about the big picture. Why does any of this matter? Why should you care? Well, first, magnets are everywhere in your life. Electric motors, generators, transformers, speakers, hard drives, MRI machines. The modern world runs on magnetism. If you did not have magnets, you would not have electricity coming out of your walls, because the generators at the power plant use spinning magnets to produce current. You would not have cars, because the starter motor and the alternator are magnetic. You would not have music from speakers, because speakers use magnets to move air. But there's a deeper reason to care. Understanding magnetism means understanding one of the fundamental forces of nature. we talk about four fundamental forces: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Magnetism is part of the electromagnetic force, unified with electricity. When Maxwell wrote down his equations in the 1,860 seconds, he showed that electricity and magnetism were two aspects of one thing. And those same equations predicted that changing electric and magnetic fields would propagate through space as waves, waves traveling at a specific speed. And when Maxwell calculated that speed, it turned out to be the speed of light. Light is an electromagnetic wave. Radio waves, microwaves, X-rays, all of it, electromagnetic. So magnetism is tied up with light, with radiation, with everything that lets us see the world and communicate across it. That refrigerator magnet is a little window into the same physics that governs sunshine and starlight. And here is something else worth pondering. When you ask why do magnets attract, you are asking a why question. And why questions are special. In science, how questions and what questions often have clear answers. What is the force between two magnets? We can calculate it. How do electrons behave in a magnetic field? We can describe it precisely. But why questions always lead you deeper. They ask for meaning, for reasons, for explanations beyond mere description. And eventually, every chain of why questions terminates in something you have to accept as a given. Why are the laws of physics what they are? We do not know. Maybe someday we will have deeper theories that explain them, but right now, the laws are the bottom floor. We rest there, not because we have given up, but because that is where the evidence has taken us. This, I think, is one of the beautiful things about physics. It teaches you humility. You can understand so much, you can explain so many phenomena, but you also learn where the edges are. You learn to be comfortable saying, this is how nature is, and we do not have a deeper explanation. That is not ignorance, that is wisdom. So let me leave you with this. The next time you pick up a magnet, think about what you are holding. Inside that simple piece of metal, trillions of electrons have their spins lined up, pointing the same direction, cooperating in a vast quantum conspiracy. The force you feel when two magnets snap together comes from the deep structure of matter, from the way electric charges interact with each other through fields that permeate space, from rules written in the language of quantum mechanics. And if someone asks you why magnets work, you can tell them it comes from moving charges, from electron spin, from the electromagnetic force. And if they ask why that force exists, you can look them in the eye and say, honestly, that is one of the fundamental patterns of nature. We describe it, we use it, but at the deepest level, it is simply how the universe is. That is not a failure to explain. That is touching the foundation. Now I want to hear from you. Think about this question and tell me your answer in the comments. At what point in a chain of why questions do you feel satisfied? When do you say, okay, that is enough for me, I understand? I am curious to know where your bedrock is.